seketika lalu ku pergi meninggalkan dirimu. Tanpa ku duga lilin menjadi barang, gurauan ku jadi dilema prasangka. Kau menyangka aku pergi karena dia yang tak.
Assalamualaikum and good day everyone. Today we will present our experiment on the Orifice coefficient. Have you ever wondered why water coming out from a small hole in a tank doesn't always flow as fast as we expect? This is because the actual flow of water is affected by friction, turbulence and the contraction of the water jet. As a result, the actual discharge is always lower than the theoretical value. To evaluate how efficiently water flows through an orifice, we use several coefficients known as the Orifice coefficients. These coefficients help engineers design hydraulic structures such as tanks, pipelines, and water distribution systems. Now, let's look at the theory behind this experiment. According to Torricelli's theorem, the theoretical velocity of water flowing from an orifice is calculated using the equation. However, in reality, the water jet becomes narrower after leaving the orifice. This narrow section is called the vena contracta. Because of the friction and energy losses, the actual flow is always less than the theoretical flow. There are three important coefficients: coefficient of velocity, coefficient of contraction, coefficient of discharge. These coefficients are related by the equation CD equals CC multiplied by CV. Among them, the coefficient of discharge is the most important because it represents the overall performance of the orifice. The objectives of this experiment are: first, to determine the coefficient of discharge; second, to compare the actual discharge with the theoretical discharge; third, to study the flow behavior of water through an orifice; fourth, to verify Torricelli's theorem using experimental data; finally, to understand the relationship between coefficient of velocity, coefficient of contraction, and coefficient of discharge.
Prepare sufficient equipment before starting the experiment. For the first reading, we measured and installed the 9mm orifice in the fitting on the right hand side of the head tank. We closed the bench flow control valve, switch on the pump and then gradually open the bench flow control valve. Then fill the tank until 35 cm. Release the securing screw for each needle and move the needle until its point was just immediately above the jet, then retighten the screw. Mark the location of the top of each needle on the graph paper. Using the measuring cylinder and a stopwatch, to determine the volumetric flow rate through the orifice by intercepting the jet. Repeat this test for lower reservoir heads at 28 cm. Repeat all of the procedure for the second orifice with a diameter of 5 mm.
So today we will discuss about the result and analysis. So here is the data from the analysis from the experiment we conduct before. So let's go to find the CD. So how to find the CD? First, we need to plotting the graph. Here is the graph. X value against the Y times H bracket half, power of half. So when we plotting, we will get the slope. Then the CV formula is slope over 2. So for the CV trial 1, we get 0.97. Then CV2, we got 0.85. So when we average it, we get the 0.91. Let's move to the 0.005 diameter. So here is the graph that we get from the data reporting, and same with before, we calculate, we find the slope and calculate in the formula CV. So the average CV is 0.90. Let's move on to the next result. Here is the result for the to find the flow rate, and also we will find the coefficient of discharge. So how to find the coefficient of discharge? We also use same method, which is plotting the graph. So here is the graph flow rates against the H power of half. So how to find the CD? CD for diameter 0.009 meter is 0.71. Then diameter CD for 0.005, we get is 0.58. So let's move on to the pipe discussion that my friend will explain furthermore.
Okay, so moving on to the discussion section. In this experiment, we evaluated the flow behavior through two different orifice diameters to verify Torricelli's theorem. As we can see from our analysis, the actual flow rate is less than the theoretical flow rate due to inevitable energy losses caused by friction and turbulence. Looking closely at our calculated coefficients for the 0.009 meter orifice, we obtain an average coefficient of velocity, which is the CV, is 0.91, and a coefficient of discharge, which is the CD, of 0.71. When we reduce the diameter to the 0.005 meter orifice, the average CV stayed close at 0.90, but the discharge coefficient dropped to 0.58. This tells us that smaller orifice generate relatively greater contraction and viscous drag, which inherently reduce discharge efficiency. Finally, minor experimental discrepancies are present. This primarily stem from parallax errors when reading the water head levels or slight manual errors when positioning the needles along the water jet trajectory. Overall, however, the direct relationship between CD, CV and CC strongly validate our hydraulic principles.
So for the conclusion, according to the result of this experiment, the flow rate affect the coefficient of discharge, and the higher this discharge coefficient will be the lower the flow rate. It was discovered that the flow rate hardly affected the coefficient of discharge if the pressure tappings were placed in a different location. We also can conclude that the increase in the diameter of orifice will increase the volume of fluid discharge as pressure acting on it increase.